Hey guys, welcome back to the third video for chapters 5 and 6. In this video we're going to cover the Poisson distribution and the exponential distribution. We do that because they're very much related. And yeah, so without any further ado, let's get on to the Poisson distribution. Poisson distribution. Consider the number of times an event occurs over an interval of time and assume the probability of the occurrence is the same for any intervals of equal length. And then that implies the occurrence in any interval is independent of an occurrence in any non-overlapping interval. That just means that each success, just like we looked at with the binomial, each occurrence, now I guess now we're talking about occurrences as opposed to successes and failures. Binomial was successes and failures, that was also discrete. This is another discrete distribution. And we're talking about occurrences in a length of time. So if we have a 10-minute length of time, how many McDonald's customers came through the drive-through in a 10-minute length of time? So that's obviously going to be a discrete random variable because you couldn't have like 3.5 people come through the line at the fast food restaurant. You could have 0, 1, 2, 3, 4, 5, 6, all the way up through, I guess theoretically infinity, but realistically, you know, some larger number. Okay, if x equals the number of occurrences in an interval, then x is a Poisson random variable, and that's described by p of x is equal to e to the mu times mu to the x all over x factorial. Okay, so that's our formula for Poisson. And then we can see that the mean is equal to mu. So that's an easy calculation. We don't have to run through that whole discrete random variable calculation. We just have mu is equal to mu, which is nice. And then the variance is also equal to mu. So then conversely, or I guess related to that, the standard deviation is once again the square root of the variance. So this distribution actually tends to be one of the easier ones from its calculation purposes, okay? And then before we get into, before we actually, it says refer to the worksheet in the example, I'm going to go ahead and show you guys these graphs and then just kind of a picture of the table. So at the bottom here are just some graphs. As you can see, Poisson is something that's going to be skewed to the right. You can see that starting to form, but certainly as the number of occurrences gets large, it seems to be more and more skewed to the right. And then above this is just a picture of one of the tables that we would use to find these probabilities. So what we're going to do is we're going to look at our worksheet here, and then I'm going to show you how to calculate this using the P of X formula that we saw on the last slide. And then I'm going to show you how to do it in Excel, show you how to do it in Megastat, and then show you how to use the table to do it. So again, obviously I don't expect you to use all of these, but I want to give you the option to use whatever you want to use. So we'll look at each and every one of them. Certainly the table gotta feel like the easiest thing to do because you can just go there and just look them up. Another really easy one is Megastat, because Megastat you just put a couple inputs in and then it just gives you the values for all x. So we'll see that here in a second. So why don't you guys turn to your worksheet. Number 6 on the worksheet, and we're just going to go ahead and get started. So A says write the Poisson formula and describe the possible values of x. Make sure the pen is working here. Okay. Write the Poisson formula and describe the possible values of x. So, as we saw on the last page, the Poisson formula is going to be e to the negative mu times mu to the x all over x factorial. So that's going to be our standardized formula, and right here we're working with a Poisson distribution with mu equal 2. So this is going to imply that p of x in our scenario is equal to e to the negative 2 and times 2 to the x all over x factorial. That's our formula. So then it says, starting with the smallest value of x, calculate for each value until p of x becomes smaller than 0.001. So all that's saying is calculate every value of x that you can until the probability gets smaller than 0.001. So we'll go ahead and do that. But I think the only reason it's asking you to do that is because that's how the tables are set up. Like, the table's not going to show you any values that are less than 0.001. So it's just having you kind of mimic how the tables are set up, and then you'll be able to then check your work by looking at the tables, and you'll see that's exactly what we'll do. So I'll just make a column for x here, column for p of x, and then we will start with 0, 1, 2, 3, 4, 5, 6. I happen to know that it's going to end at 8 just because I've already ran the calculations. So we'll do our calculations over here. P of 0 is going to be e to the negative 2 times 2 to the 0 over 0 factorial. And this is just then going to be e to the negative 2, because 0 factorial is 1 and 2 to the 0 is 1. So it's going to be e to the negative 2. And we run that calculation in our calculator. 1.353. So we do 1. It's going to be e to the negative 2 times 2 to the 1 all over 1 factorial. So yeah, like I said, by definition, 0 factorial is 1. 1 factorial is also 1. So this is going to turn out to be 2 times e to the negative 2, which is just going to be 0.270. It looks like it's 0.2707. Okay. And p of 2, e to the negative 2 as always, and times 2 to the 2 and 2 factorial. So it looks like we're going to be getting 4 times e to the negative 2 all over 4, which is then just going to be e to the negative 2. Or, sorry, 2 factorial is just 2. So it's going to be 2 times e to the negative 2, which we actually just calculated, right? So that's going to be 0.2707. And we'll just do one more here, because I know you guys know what you're doing now. Times 2 to the third, 3 factorial. And this looks like it's going to be 8 e to the negative 2 over 3 times 2 times 1, which is 6. So 4 thirds times e to the negative 2. And that is going to be 0.1804. Okay. So I'm not going to bother with the math, but I will write the rest of these numbers down. You guys can do the calculations on your own to verify. Four, 3, 6, 1, 1, 2, 0. Oh, so that's for 6. Okay, so that's going to be our P of x's for all of those. Okay, and so we've now done part B, and now let's just go to an Excel sheet and verify that these things make sense. Okay, so we are going to look at this Excel sheet. I've made columns for x, for mu, I guess, not n, mu, and cumulative or not. I think you guys remember in the last video, that's going to be a true or false value, or a 0 or 1, false being 0, true being 1, and cumulative means, are we going to be looking at the probability of one specific instance or everything up through that specific instance? So for this one, we just want to calculate what the specific instance is. So in our problem, we had mu equal to 2, and let's just check one of the probabilities. So we'll put 0 in for x, and then we would write out equals Poisson dot dist. Okay, we're there. And then click on the cell with our x, comma, click on the cell with our mean, comma, click on the cell to signify whether it's cumulative or not. And we're going with not. So 0.1353. So we go back over to our worksheet, 0.1353. Let's check x equal 1. 0.2707, 0.2707, 0.2707, 0.2707, and 0.1804 and 0.1804. Okay, so that works. Okay, so we see that we can do this on Excel. Now I'm going to show you how to do it in Megastat, and then after Megastat we'll look at just the tables. So we go to Megastat, probability, discrete probability distributions, and over to Poisson. Okay, and it's asking for the mu, or the rate of occurrence, which, those are the same thing. So mu is equal to 2. And then maximum x value, that's optional. So I guess because we wanted to go up to 8, let's go up to 8. But because Poisson is interesting because it's discrete, but theoretically, like the numbers, it can go up to infinity, right? It's countable, but it'll just go on and on forever. Okay, but we'll just cap it at 8. So let's see. So we hit OK. It'll spit us out an output page. Here we are. These numbers look very familiar, so that's good. And you guys can go ahead and cross-check those with what we did on the worksheet. But those look right. So there's that. And now let's go take a look at the PDF, or the tables. Okay, so in the back of the book, I don't know what page this is on, but I know that it's right after the binomial tables. You find the Poisson tables, and this is how you read the Poisson tables. We first look at the top, and we look for mu. Okay, and now we're going to be looking for a mu that's equal to the mu that we used in the problem. So right here, we don't have it. We're looking for the number 2. There's the number 2 right here. And then we would just then look at our x values on the left-hand side here. So it looks like it has 0 through 8. Okay, and so then here is our column over here. And we have 0.1353, 0.2707, 0.2707, 0.1804, all the way on down, and these are exactly the numbers that we got. So that's how you use the table. And again, we'll be using this more in the review, and I think in the review maybe I'll try to use one way of doing it per part of the problem. So in one part I'll use the table, in one part I'll use Excel, one part I'll hand calc, and we'll see how that goes, just to kind of remind you guys how to do it. And I'll try not to be confusing about it, but I just want to stress that, like, you use whatever you want to use, like whatever you feel most comfortable using, that's what I think you should use, okay? All right, so that's how we find that. And now we're going to move on to parts C through J in the worksheet. And again, I think we're just going to go ahead and skip graphing it. It's asking us to graph our results. That's not something I'm going to ask you to do. If it were to ever be asked, like if graphing your results were something, then yeah, I'm sure you guys could figure out how to do it. I'm not horribly worried about that. Or if it's on like the case or something where it needs to like look professional, I think you just saw that in Excel, Megastat just spits you out a graph. So you could always use something like that. Parts D through J, like I said, not worrying about the graph. There we are. Sorry, I'm getting my pen ready here. So, okay, so part D is asking for what is the probability that x is equal to 2? Well, we just go ahead and look in our table. We actually already calculated that probability. So we scroll up here in our table. The probability that x is equal to 2 is 0.2707. So that's kind of nice. So we already have that done. So 0.2707. Let's look at B. That was D, and this is E. E is asking for the probability that x is less than or equal to 4. Okay, now remember, for discrete distributions, the or equal then is very important because like this is going to include 4, which in and of itself is a x value that needs to be looked at. Okay, so for a discrete function, the probability that x is less than or equal to 4 is going to be probability that x is 0. Erase that real quick. Plus the probability that x is 1, plus the probability that x is 2, plus the probability that x is 3, plus the probability that x is 4. And so that's what the probability that x is less than or equal to 4 is. So we just go to the table, we find all of these values, and we look them up, or we add them up. So probability that x is equal to 0 is 0.1353. Next is 0.2707. Next is 0.2707 again. Then 0.1804. And then 0.902. Or, sorry, 0902. We add all those up and we get 0.9473. Okay, let's look at F. F is now the probability that x is less than 4. Okay, so not the same thing that we just saw. So the one thing that's different is that we don't include 4. So we're literally just looking for the probability of x equals 0 plus the probability of x equal 1 plus the probability of x equal 2 plus the probability of x equal 3. Now logically, so we could add up all those again. We could do that. Or we could just say, well, we know what the probability of x is less than or equal to 4 is, and now all we have to do is minus out the probability that x is actually equal to 4, right? Because that's what this is. the probability of x less than 4 is essentially the same thing as the probability of x less than or equal to 3, right? Which would look just like this same thing. So we could just take what we previously did and minus off the probability that x is equal to 4, which is just 0.0902, and then that's going to equal 0.8571. Okay, and EFG, so we're on G now, and then find the probability that x is greater than or equal to 1. And then it also wants us to find the probability that x is greater than 2. So the one thing I noticed about greater than or equal to 1 that is going to be the easiest way to solve this. So first of all, because there's no limit to how high the Poisson can go, like we've sort of created an artificial limit in that we decided to stop calculating values once they got to a certain small point, right? We sort of stopped at x equal 8 because I think we got to 0.0009, so we got to some very small number. Whenever we're doing like a greater than probability, one thing that we know that the total probability in any situation is going to be 1. It's going to be equal to 1, right? So when we have something that's saying, we'll find the probability that something is greater than another number, such as what we have right here. We have a greater than or equal to with the 1. We also have a greater than with the 2. The easiest way to do these is to not add up a bunch of probabilities, but it's to say, okay, well, we know that the total probability is 1, and now we're just going to minus off the pieces that don't fall into that range. Right, so the pieces that fall into x is greater than or equal to 1, the pieces that fall into that range are going to be 1, 2, 3, all the way on up to every x value possible. So the only thing that doesn't fall into that range is 0. So the easiest way to calculate this would then be, okay, well, it's just going to be the total probability of 1 minus the only thing that's not in that range, which is probability that x is equal to 0. Which we know that, and so it's just going to be 1 minus 0.353, and that is 0.8647. Okay, and then we do this one a similar way. Even though we don't have like the inclusive greater than, it's not greater than or equal to, it's just greater than. We just decide, okay, well, we're going to minus off whatever is not included in that range, right? So we just say, well, this is just 1, the total probability, minus everything that's not included in that range. So we know that 0 isn't included in that range. So minus probability that x is equal to 0, minus the probability that x is equal to 1, and then also minus the probability that x is equal to 2. Because we're not including 2, we're just saying everything greater than 2. So it's actually starting off at 3 because we're discrete here. So we minus that off as well. So, and this was way preferred to, just adding up probability that x equals 3 plus probability that x equals 4 plus probability that x equals 5 all the way on up to infinity, essentially. So it's going to be 1 minus 0.1353 minus 0.2707 minus 0.2707 again. And that is going to give us, if I can find it on my page, 0.3233. Okay. Okay, move on to H. So now we're going to be doing the probability that x is between 1 and 4, inclusive on both ends. All right, so this just reads probability that 1 is less than x, or is less than or equal to x, is less than or equal to 4. That just means that including the endpoints, so including 1 and 4, x is between 1 and 4. So this would just be then adding up all those points in between. So this would be equal to the probability that x is equal to 1 plus the probability that x is equal to 2 plus the probability that x is equal to 3 plus the probability that x is equal to 4. So we have all these pieces, 0.2707. I don't know why that thing decides to disappear. Um, 0.0902. And this is equal to 0.8120, I believe. Okay, so there's an alternative way to do this. I'll just say alt method. And that would just be to take the top end, cumulative, and say the probability of x is less than or equal to 4, and then minus off whatever is underneath that doesn't fit into the range, right? So we could say, because we actually already calculated this. This was in part E. And in part E, that was 0.9473. And then the only difference to this range versus this range is the inclusion of probability of x less than 1, which is just probability that x is equal to 0. And we know that that is 0.1373 or 0.1353, which then we calculate that, and that's 0.8120, which is the same thing that we got up here. Okay, so I'll let you guys finish up on I and J. That is a lot of problems that we're working through, and yeah, if there's any questions on I and J, please let me know in the discussion forums, and that's that. But right now, I guess we'll move on to exponential. Okay, so exponential distribution is now a continuous distribution, and this is very much related to the Poisson. Okay, so it says suppose that some event occurs as a Poisson process. Okay, so similar to what we were talking about last time, the Poisson process is counting the number of occurrences something happens in a time interval. So this is going to be a little bit different with exponential. Okay, so that is the number of time an event occurs in a Poisson random variable. For this, let x be the random variable of the interval between successive occurrences of the event. So rather than us counting the number in a 10-minute period of drivers that come through a McDonald's drive-through, the exponential variable is saying that what is the time that occurs between successive people that come through the drive-through. So really we're just talking about one occurrence to one other occurrence, and then the time between those two. Okay, so the time is then now our variable. That's going to be our x variable, essentially. And time is measured in an interval, and that's why it's continuous, okay? So yeah, it goes on to say that the interval can be some unit of time or space, and that way we know that it is described as an exponential distribution with parameter lambda, which is the mean number of events that occur per given the interval. Okay. And right here we have f of x. F of x is equal to lambda e to the negative lambda x. And the way that we find a probability is this formula right here. So it's a probability of an interval. And we go on, we have that formula expressed again right here. So here is, let's draw. So this was our p of x or our f of x, however you want to look at it, for the continuous random variable that's exponential distribution. This is the way that we would find an interval for probability. This is the way that we would find an interval that isn't between two two numbers. So this would just be the bottom end of the function, and this would be the top end of the function. So x is greater than some number, x is less than some number. And now again, in the continuous, the less than or equal to or greater than or equal to is not important. That's only important in discrete. Okay? And then here's how we find our mu of x. It's just going to be 1 over lambda, and then sigma x is 1 over lambda as well. So very easy formulas for mean and standard deviation. Okay, and I believe that is our last slide for this. It is. So let's look at the exponential distribution and go to number 7 on your worksheets. Suppose that the random variable x has an exponential distribution with lambda equal 3. Okay, so this is page 248, number 649. Write the formula for the exponential distribution, exponential probability curve of x. What are the possible values of x? Okay, so I'm just going to do A right here so I don't run out of room like I did last time. And using the formula, we get f of x is equal to lambda, which is 3, e to the negative lambda x, and this is for all x greater than or equal to 0. And then we say it's worthless otherwise. So 0 otherwise. And that's just going to account for negative x values, because we can't have like negative space or negative time or anything like that. Okay. Sketch the probability curve. Sure, fine, we'll do that this time. Okay, so that's supposed to be a straight line with at 0 with height of lambda, so 3. It's just going to be kind of a smooth-ish curve going down like that. There are better examples of this in the book, so feel free to open up the ebook or look at the slides. I think I had some graphs in the slides. But yeah, so obviously if you need to present it on a test, it should look better than that. But that's about all I got with writing with the pen here. Okay. So as always, it wants us to find probability. And I'm going to go ahead and show you how to do that probability using the formula, using Excel, using Megastat, and actually there are no exponential tables in the back of the book, so we'll just be using those three methods, okay? So just the formula, Excel, and then Megastat. Okay, so C is asking us, what is the probability that x is less than 1? Okay, so we would go back to our sheet, and we would see that the probability that x is less than or equal to anything is going to be 1 minus e to the negative lambda and that number, c. Okay, so this is going to be 1 minus e to the negative 3, because that's our lambda, times that number, so 1, which then is equal to 1 minus e to the negative 3. And then if we calculated that all out, that's 1 minus 0.04978, which is equal to 0.950, roughly. Okay? So in D, we're going to go ahead and calculate D just as we would. So D is probability that x is between 0.25 and 1. So we go back to the PowerPoint and we find the formula for this. That's right here. And that is just going to be e to the negative lambda a, so the bottom of the range here, minus e to the negative lambda b, so the top of the range here. Okay? So we say e to the negative 3a, which is 0.25, minus e to the negative 3, because that's lambda, of 1. Okay, so this is going to be e to the negative 0.75 minus e to the negative 3, which using our calculators we can figure that out, and we get 0.4723 minus 0.04978, which we actually knew that from the last problem, and we get roughly 0.423. Okay. I guess we'll go ahead and just calculate. We'll just hand calc all of these, and then we'll go do some of them in Excel. And now it's asking us the probability that x is greater than or equal to 2. So we go back here, we look, greater than or equal to is just going to be e to the negative lambda c. So e to the negative 3 times 2. So e to the negative 6. And e to the negative 6 is 0.002. Okay. And then so F says calculate the mean variance standard deviation. So our mu of x, we just go back to the table. So mu of x is going to be equal to 1 over lambda. So we know that it's equal to 1 over lambda, which lambda is 3. So it's going to be 1/3. That was easy, right? And then we also have a formula for sigma x for our standard deviation, and that is also going to be 1 over lambda, so 1/3. And then we know that variance is just standard deviation squared. So then that's just going to be equal to 1/3 squared, or 1/9. Okay, part G. Find the probability that x will be in the interval mu of x plus or minus 2 sigma x. Okay, so we just calculated what mu of x is. So mu of x is equal to 1/3, and sigma x is equal to 1/3 as well. So let's just calculate what this interval would be. So the interval of mu of x plus or minus 2 sigma x on the bottom end. So we'll just say 1/3 minus 2 times 1/3. And then on the top end is going to be 1/3 plus 2 times 1/3. Okay, and that's going to equal, what does that equal? Negative 1/3 to looks like 3/3 or 1. And we know that this function is only defined for x values that are 0 and greater. So this interval can kind of go to 0 to 1, right? Because negative 1/3 doesn't exist on the interval anyways. So really we just want to know what the probability from 0 to 1 is. So we're going to take this down here. So the probability from 0 to 1 is just going to be the probability that x is less than or equal to 1. And lo and behold, we've actually already solved for this, right? So we solved for this in part C, and because we solved for it in part C, it is just, in part C, it is 0.95. Okay, guys, if you have any questions about exponential or Poisson or really any of the concepts or the problems, write about it in the discussion forum. I will answer the questions as soon as possible. I'll get the review up as soon as I can, but I wanted to get these lectures up as soon as possible, and I just was not able to get the review done now. So the review should be up in the next couple of days. All right, that's that. Thanks so much for your time, and yeah, till next time.